This program is brought to you by Stanford University.
Native client. So native code in a web browser, what's the big deal? I mean, actually, ever since NP API and ActiveX were introduced almost 10 years ago, you've been able to use native code in the web browser. Of course, probably most of you don't, and the reason is because there's a lot of security issues with using it. The problem is that NP API and ActiveX and giving you native code, they actually give you two things. Yes, they give you direct access to the CPU, but they also give you direct access to the native operating system. And therein lies the problem, because that's the way that a lot of viruses and other malware basically cause programs to do things you don't expect, like joining a botnet or sending your passwords off to some evil person who's going to do who knows what. So the key observation in native client is that there isn't actually any reason why CPU access and operating access need to be inseparable. We can give you one without the other. And so our goal in this project is to give you only direct access to the CPU. You can run native code at full speed, but no access to the operating system. And that way, we're hoping to give you native code modules that are as safe as JavaScript or the other kinds of web technologies you probably take for granted. So let me be very specific about some of our goals. We want safe execution of untrusted x86 native code. Now, there's other instruction sets in the 64-bit variant. We like those are important too. We just aren't working on those, aren't providing those yet. And we want performance to be about the same as native code. And I'll give you some details on the performance impact of the system at the end of the talk. The next few things are actually things that you should expect from any decent web technology. OS and browser portability. You don't have to worry about which browser you're running in. And it should be trustworthy. There's some specific things we're doing in native client to try and make it more trustworthy. Firstly, we're working very hard to make the trusted code base as small and simple as possible. And actually, we're making the system open source, so you can go check it out yourself if you wonder about security properties and understand exactly how safe it is. Another really key thing about what we're trying to do is we're trying to complement, not replace, existing web infrastructure. We don't want to replace JavaScript, for example. We think JavaScript is great for a lot of things. We just want to enhance it with the ability to do high-performance kinds of computation when it happens to be useful. Now, I also want to explicitly mention some non-goals of the project. We are not able to support execution of existing binary code. We might have liked to do that, but it just seemed hard. And so we had to give up some stuff, so that was one of the things. You have to recompile. Also, instruction set portability. Now, in the fullness of time, we believe the web is portable, and that includes instruction set as well as other things. But in this first system, in our first attempt to create something useful, that was one of the things that we decided to compromise on. So a lot of this is a lot more tangible if you actually can see what's happening, see it in action. So I have a little demo here. This is something you're going to actually download and build as a part of the native client open source release. And it's a Mandelbrot viewer from MIT called Chaos. And we're just cycling through these different Mandelbrot type images. There's nothing that amazing in any of that. The place where it gets interesting, though, is when we start interacting with it. And it's this kind of ability to actually animate and pan in real time that's not something you'll find in any application implemented in JavaScript, at least not with this kind of frame rate. Those of you who are familiar with Mandelbrots and those sorts of things will also recognize that generating these kinds of images is actually very computationally intensive. And so if I do this long enough, my fan will go on, the machine will get hot. It really is completely non-trivial. Now, my daughter loves this. However, she's actually 4.5, and I expect some of you would probably not find it quite as interesting. And so this is one I don't do with my daughter yet. But we've also set this thing up so it can run Quake. And if any of you are really hardcore gamers out there, this might bring back some fond memories of the 90s. But it's actually, in terms of game technology, pretty primitive. But the important point is that, oh, right, I can't see my thing here. Single player, new game. We can actually play it. We can interact with it. You know, you can run around. I'm not a very good Quake player. I usually just run straight into the lava pit. And, oops, where am I? There we go. There's the lava pit. Woo! Okay. So the key things to understand about that is it's actually performing at a pretty close what you'd get to compiling natively. It's a frame rate of about 45 frames per second on this machine. It's doing a full physical simulation, relatively coarse, but it's doing a physical simulation of how objects interact when the guy runs into a wall or, you know, firing bullets and things like that. And that's fairly interesting computationally. And of course, it's doing the real-time animation. So this is a kind of thing that we assert you just can't do in JavaScript. The computational performance is not there. And it's the kind of thing that we'd like to be able to make common if we can convince people to get comfortable with this technology. So back to the regularly scheduled program, let's talk a little bit more about the details. I've shown you maybe some examples of why you might want native code in a browser. Let's think about what the problems are. Okay, so I want to start explaining the system with a little kind of a hypothetical application. Imagine you wanted to create this, let's say it's a global cooling game, and you were going to use native client modules to make it particularly wonderful. Okay, so someplace and obviously, you know, I'm assuming you'll want to run this in a web browser. So someplace in your HTML, you might have an embed tag, or maybe you could also use an object tag today that will tell the browser to load a native client module. Now, before any of this will work, you have to have decided to install the native client plugin. This is a piece of trusted code. You had to click OK someplace in order to get it installed, presumably. And it can do anything it wants to your computer system. But it's open source. You know, maybe the fact that it's from Google might make you feel comfortable, maybe not. In any case, you can look exactly at what's in it and understand whether or not you want to trust it or not. So this thing, the native client plugin, is responsible for pulling down untrusted native code from the web and running it if it thinks it looks safe enough. Okay, so perhaps our global cooling game is going to be using a physics simulation, and that's the untrusted native code module you want to use. Now, if the untrusted code wanted to do something evil, then the first thing that's going to happen is we're going to check it out and make sure there's no sharp objects. And in the case that there were sharp objects, things that we decided aren't safe, it would not be allowed to load. But the physics simulation, let's assume that we looked it over very carefully. It looks like it's OK. So we're going to decide, OK, we'll go ahead and let the browser run this. Now, a key thing to understand is we're launching this in your browser, native code, with no pop-up boxes. It's not going to say, is it OK to run the physics simulation for the global cooling game. It needs to be as safe as the JavaScript and the other things that you use automatically. So we've loaded the code. We think of it as kind of being in a jail because there's a bunch of stuff that we're not going to allow this untrusted native code to do. But nonetheless, it's running. It's got full access to the CPU. And once it's instantiated and it's in this little jail, we'll connect it up so it can communicate quickly with the web browser. And that actually includes shared memory support for high throughput kinds of computations. And now you're ready to go, and the game can sort of start and do its thing. So that's sort of at a high level how the system fits together. Now, a couple of other nuances I want to mention. You can have multiple native client modules. And the browser, through your JavaScript, you can set it up so that they can talk to each other. Okay? We also have sort of foreseen the possibility that there might be other trusted code that would be able to communicate with a native client module using the same communications infrastructure that we've created for these new kinds of modules. For example, you know, someday it might be nice to have a trusted module that would let you interact with a local file system. Maybe it's going to enforce some sort of policies, like a maximum amount of space or not being able to touch certain files or something like that. And so that could be a trusted module that the native client code could use through an API and communicate through one of these interfaces. And that's all kind of hand-wavy right now. You won't even find that in the open source release. But it's a part of the architecture that we're planning, is to be able to create things and hook them together like this. So what do I mean when I say safe? I think I've said safe at least 5 times so far. Well, our intention is that we want to prevent side effects except via explicit secure interfaces. Now again, this will be clear if I make it a little bit concrete. So let's take a look at an example of a bad program. This program, if you run it on your typical Linux machine, in particular if you ran it the way we set things up at Google, would be the beginning of a very bad day, right? It's going to try and delete all of your files. Most viruses are more sophisticated than this, but this is a good place to start. So a native client module needs to make this impossible. If you download a piece of native code that wants to do this, no way. The native client infrastructure needs to prevent that. If only it were this simple. It's obvious just reading this code that you wouldn't want to run this program. But there's all sorts of variants, in particular on the x86 architecture, that make it hard to do this in a straightforward way. In particular, dynamically generated code, code embedded in data, and overlapping instructions are all problems. And to make this more concrete, let's take a look at another version of the same program. This actually is going to do the very same thing. You can see I've got the arguments to the system call down here, but it's hard to see where the system call is happening. And actually, it's hard for a disassembler or analysis tool looking at this program to see where the system call is happening. And that's one of the reasons why this kind of technique has been challenging in the past. Now, I've highlighted a few things to make them clear. The first line that I've highlighted there is creating a constant. And you'll notice it's initialized with a kind of a curious hexadecimal value. It turns out that embedded in that hexadecimal value is a system call instruction. And that constant is going to be embedded in a longer instruction that's going to initialize that constant someplace on the stack. Okay? But the key thing is that we have the bytes for a system call instruction in the instruction stream. Okay. The next line is actually computing the address of the system call instruction relative to the beginning of the procedure. And then this is just stuff that's setting up the system call so it'll look like a system call to the Mac OS kernel. And this is a jump instruction that's going to jump through the address that was initialized there to the system call instruction. Okay? So, in other words, this is just doing exec VE of what we wrote down here below. It's the very same program, but it's structured in such a way that it's basically not. It's an example of what makes it difficult to automatically recognize when a program's going to do invoke a system call. So control flow is one thing we need to constrain. We need to be able to tell where the program's going to jump to and make sure it never executes instructions like the system call instruction that we've decided is special. There's some other things we need to constrain, too, related to data references. Basically, we want to contain the loads and the stores of the program to make sure they never look at anything outside of the sandbox that we've defined as safe, that we've set up as safe. So native client modules should never be able to damage other computations on the system. If this were running in the same address space as the browser, we need to prevent it from overwriting stuff on the stack of the browser, for example. And one assumption which we make in all of this system is we don't assume that the operating system is cooperative or even bug-free. This, as it turns out, maybe it sounds a little bit paranoid at first blush, but it really is a basic requirement for portability. You can't assume operating systems always do X if you want to, in general, be able to make your system portable. So that's an important part of it. And in particular, we imagine the possibility that the operating system might decide to load arbitrary things into the address space of all the processes on the system, things which you would not want the native code to have access to. And so that's a part of the reason why we're creating an infrastructure that actually creates a protection subdomain inside the process where the untrusted code is going to be running. Let's see. So wild writes are one problem. Devious reads are another example. We don't want information leaking out of this thing. And so we're going to do that by containing the memory and only letting the untrusted native code look at memory that's effectively been scrubbed. Mendel.
So does cooperative, not cooperative, mean that you support a malicious operating system?
Well, let's see. I don't know. Maybe it'll become clearer as I proceed. If the operating system were malicious in a very deliberate and premeditated way, I don't think there's anything that you could do to prevent them from interfering. But yeah, we assume that the operating system is neutral at best, and try and not be super sophisticated with how we use the operating system, but really only use facilities that everybody needs to use. I mean, that's at least our objective. I'll come to some detail later on about things we wish operating systems would do better, though. So here's sort of a catalog of threats that we're interested in and concerned about. The first set, the primary threats, we really want to make those extremely difficult, at least as difficult as they are in a browser environment from JavaScript today. The secondary threats are things we're going to try and prevent and sort of mitigate the impact of, but we may not be able to eliminate them completely. So code integrity, control flow integrity, and data integrity are some mechanisms that I'm going to talk about next that basically give us the top 4 things that make the primary threats, things that we control in the system. For the secondary threats, we don't address those as directly. We have timers that will kill a native client module if it seems like it's using up too much CPU without doing any useful work. For the memory leaks case, we're just going to place a finite limit on how much memory a native client module can use. Corrupt output is sort of a tricky one. If you imagine exchanging data structures between a native client module and some trusted code that was going to do something with it, maybe it's an argument to a system call eventually. Well, you want to make sure that the arguments that are passed into that trusted code have been sanity checked before the trusted code trusts them. NP-API is another example where this might come up, arguments passed into NP-API, in the NP-API interface. And then covert channels. In honesty, we're just sort of punting on this one for now. We decided that all the other threats were so much more of a risk that the covert channel issue is probably not something that we're going to deal with in the short term. And so materially what that means is that we left the read timestamp counter instruction in the set of instructions that we support. So we do allow people to get fine-grained time and cycle accurate time. So next thing I want to do is tell you a little bit about the actual mechanisms we use. How do we prevent side effects that we don't want to be able to happen? And the mechanisms are sort of structured into 2 major pieces. One we call the inner sandbox, and the other we call the outer sandbox. Without delay, let's talk a little bit about the inner sandbox. The inner sandbox applies 2 technologies that have been around for a really long time. The first one is software fault isolation. This was introduced by some seminal work by Wabi, Luco, Graham, and Anderson back in the 90s. And it's a really neat technique for constraining code sort of operating at the machine level. And the next mechanism is segmented memory, which all of you should recognize from your architecture classes. Hopefully they still teach segmented memory, right? And it still exists on,
Aren't they getting rid of it? Like it's not in 64-bit mode?
We'll come back to that. It's still in 32-bit mode anyway. So that's the inner sandbox at the highest level. It's been carefully designed to minimize operating system dependencies, and that helps us because we get a portable sandbox. It behaves in the same way on all systems. And it's relatively immune to operating system defects. In particular, when this thing is up and running, once it's all set up, there's no interaction with the operating system at all. It is secure all by itself without needing anything in particular from the operating system, except for the most vanilla sorts of things, like your memory map doesn't change randomly and arbitrarily while you're running. Now, there is one caveat. In order to use x86 segments, you need to initialize a structure called the local descriptor table, or LDT. And actually, LDT system calls for doing LD, since it's a privileged instruction, it has to be done in the kernel. You have to do it through a system call. System calls are totally available and in the clear on Linux and Mac OS and all the old versions of Windows. But it turns out they seem to have eliminated the system call in 64-bit Vista. And so that's sort of a caveat. We're working on that one. And we'll get back to you when we decide what we're going to do. But since nobody's using 64-bit Vista, it's not a super big deal right now. It is something that we are thinking about for the future. We do require a modified compiler, assembler, and loader. And as I show you some more of the details of how software fault isolation works, I think you'll understand why. The key point I want to make now is the modifications are simple and open. It took about 1,000 lines of patches to the GNU tool chain in order to get it to generate proper native client code. And we think other compilers would probably be easier, but we haven't done them yet. So it's kind of an exercise for the reader, perhaps. And the runtime overhead is very small. And like I said, I'll show you some numbers about that later on. So let's first talk about segments in a little bit more detail. The native client address space, the address space that an untrusted module can use, is bounded by x86 segments. And in particular, the code segment is controlled by the CS segment register, and we're just going to set it to exactly the code that has been downloaded and checked by the native client system, and not let any execution happen anyplace else. So that's one critical part of bounding where control flow can go to within this region that we've inspected very carefully. And then we use the data segment registers to restrict other loads and stores and stack memory references and such. And the address space layout is pretty ordinary otherwise, but the key thing is that we've got the segment register protection that's going to bound where loads and stores can go. That actually allows us to get a much more efficient implementation of software fault isolation than what was originally described. Since, because the original software fault isolation system used instruction masking, used masks on addresses to bound the region. So it basically took an extra instruction in every one of these loads or stores or control flow operations that they wanted to control. Whereas in this case, we just use the segment registers, and it's part of the reason why we can get our overhead as low as it is. So that's segments. That's all I'm going to say about segments for now. Let's talk a little bit about control flow integrity next. Now, the key thing that we want to achieve here is that for every control flow instruction, every jump, every call, every return, we want to know that the place we're transferring control to is safe, that it's an instruction that we've looked at, okay? And so the first thing that we're going to do when we get a native client module and we want to decide whether or not we run it is we're going to disassemble it from top to bottom, and we're going to see, and we're going to use that to define the address of every instruction that possibly can be executed. In other words, if there's an address that's sort of in the middle of an instruction someplace, that will be off limits. We will not allow control flow to transfer to the middle of an instruction. So next, we need to look at the control flow operations in the program and see that they actually are going to safe instructions that we've inspected. Now, for control flow that can be analyzed statically, where the address is clearly indicated in the instruction, in this case, for example, a call to address 8EF40, we just look at address 8EF40 and make sure it's an instruction that we've looked at and is safe. The trickier case is when you have indirect control flow, like this call through a register. In that case, we use the classical sandboxing approach. And in addition, we require that native client text must be aligned to 32-byte blocks. We actually give you a choice of 32 or 16-byte alignment. But the text has to be aligned. And then all indirect control flow needs to be aligned as well. And that's this AND instruction here. So we're going to replace this call instruction with a sequence that looks like this. The first one loads the effective address into EAX. The next one ensures that EAX is 32-byte aligned. Okay, so we know that when we get to the call here, we'll never be able to transfer to control to any address that's not 32-byte aligned. And since we've earlier checked that all the 32-byte aligned instructions are okay, we know that control flow will always go to a safe address. Okay? So that's the essence of the way we're doing control flow integrity in native client and how we're making sure that we only transfer control to valid instructions. So this next slide goes through the full set of rules that the native client validator enforces in order to make sure that control flow is safe. And in the technical paper that's on our website, we actually provide a proof by contradiction that asserts that this is actually adequate, that this provides the property that we only execute instructions that we've inspected. But to go through these points one at a time to make things clear, firstly, like I mentioned, all valid instruction boundaries are determined by a top-to-bottom disassembly of the text segment. And that defines the only instructions that we're going to allow to be executed. Next, all aligned memory addresses must be a valid instruction boundary. In other words, if in this top-to-bottom disassembly we see an instruction that straddles a 32-byte boundary, the module is unsafe and we refuse to execute it. Next, computed jumps use sandboxing to force alignment, like the example I just showed you a moment ago. Next, branch targets that are within the code segment, and that's just segmentation is going to force that to be true. So we can't branch outside of the code that we're statically checking. And then we're simply going to forbid mixed text and data, overlapping instructions, dynamic code generation. So once we've defined a text segment, there's not going to be any way to add anything to it. Overlapping instructions, we kind of talked about that. And for mixed text and data, well, there's no reason why you can't use something that we've disassembled as a data word. But what we don't allow is to have arbitrary data in the text segment. Arbitrary data that could have, that could fail to satisfy these properties that we're talking about. So those are the rules that we require, and these are the rules that the validator enforces. Okay. So once we now the point of all of those rules is to make disassembly reliable, to make sure that we see every instruction that can possibly be executed by the untrusted code. And with reliable disassembly in hand, there's a bunch of other things that we can actually do. For example, we can arbitrarily remove instructions from the instruction set. Now, of course, we're not arbitrary about it. There's some very specific things that we leave out. One of the more curious ones is the return instruction. The return instruction, of course, is indirect control flow. Now, perhaps you might imagine, well, why not just sandbox the return address? Well, of course you have to sandbox the return address. But if you sandbox on the top of the stack and then return from this top of the stack, that's in memory. And since we're really keen on supporting multi-threaded programming, you would have the possibility that one thread could clobber the return address between when you sandboxed it and when the return instruction happened. So instead of using the return instruction, we require that you use a pop and a jump. And that's just one example. Of course, we disallow the system call instruction. We've got a little bit of an issue with hardware exceptions, too. The problem being that when a hardware exception happens, this is like a division by 0, the first thing the operating system does is, so the hardware pushes all of the hardware state onto the stack. Then the operating system, the first thing it does is looks at the state on the stack and says, what was the machine doing when this happened? And so that it can deliver the exception as appropriate. Well, the problem is that none of the operating systems are expecting segment registers to be used. All of them today say, whoa, this looks really messed up. I have no idea what this process was doing because its segment register has a strange value. And so they just give up. They kill the process and everything's done. So that's an example of one of the things we'd like the operating systems to fix someday. But for the time being, we have no choice but just terminate the process. Now, I do want to note in passing that although we can't handle division by 0, segmentation faults, those kind of hardware exceptions, C++ exceptions are just fine, as defined in the language, catch, throw, that sort of thing. Turns out those all happen at user level, and there's no operating system support required. So those ones are just fine. Now, otherwise, in terms of omitted instructions, we also left out most of the instructions that were omitted in the x86-64 instruction set. The reason being that we are actually concerned about hardware errata, that is, cases where the hardware actually has a bug and misbehaves for some particular instruction or sequence of instructions. And the instructions that were omitted in x86-64, mostly they were omitted because nobody used them, and they weren't really very useful in the first place. Well, if nobody's using them, then they're kind of that much more vulnerable to being implemented or sloppily or not tested carefully. And so we decided it was better off just not to have them at all. Another set of behaviors, another set of instruction set restrictions that we impose is prefix usage. Now, for those of you who are familiar with x86 machine code will know that in principle, any instruction can be enhanced with prefix bytes that you add before the instruction and that have semantics of things like lock, make the instruction atomic, or or maybe use a 16-bit addressing mode or that sort of thing. In practice, in principle, you can have any number of these prefix bytes and you can append them to any old instruction. In practice, actually, that's not really true. There's only a small set of cases that are actually useful and make sense. And so native client enforces those. And in a more extreme case, we actually only allow one prefix byte per instruction. We couldn't really find any useful instructions that use more than one prefix byte, and so we decided to have that as a rule. We've disallowed some prefixes entirely, such as 16-bit addressing. Now, we do allow the prefix for 16-bit data, but we do not allow the prefix for 16-bit addressing modes. And then we further restrict prefix usage only to known useful combinations. So for example, we don't let you use the lock prefix with instructions for which the lock prefix is not useful. Now, some people have thought, well, geez, this seems pretty heavy-handed. I mean, it's not really your instruction set, is it? The problem is that before we had these restrictions, we were actually running in our test cases, we were running into situations where you could actually cause the machine to halt in such a way that you would have to power cycle it in order to get it back. And once we added these restrictions on prefix usage, that didn't happen anymore. So we think there are errata and that are subject to prefix usage. And by restricting prefix usage in this way, it's really deliberately reducing the attack surface to as small as possible. Now, with all these restrictions in hand, I do want to point out that we went through a lot of trouble to support instruction set extensions, things like MMX and SSE instructions. We think that they are very important going forward in terms of getting peak performance out of these machines, although it did take a little bit of work. I mean, for example, imagine you have a computer, perhaps a kind of an old computer at home, that has MMX instructions but doesn't have SSE instructions. And then you try and run a piece of code that wants to use an SSE instruction. Well, the problem is your hardware has no idea how long that instruction is, right? Now, if it had SSE support, of course it would know how long. But without SSE support, you know, it could decide it's a 1-byte no-op or, you know, some other random length. And the indecision about the length of the instruction is an opportunity to sneak one of these illegal instructions that we don't want to allow into the instruction stream. So we can't let that happen. We can't let your hardware that doesn't support SSE try to execute an SSE instruction. And the way that we do that is while we're disassembling and inspecting the code, we also are keeping track of what instruction set extensions your hardware supports. And if we see an instruction that's not supported on your hardware, we'll overwrite it with 1-byte halt instructions, such that if you ever try and execute those bytes, the module will be terminated abruptly, with prejudice perhaps. That, again, might seem a little bit heavy-handed, but you know, there's sort of a philosophical thing. We cannot force people to write correct code. We can take whatever code they give us and try and make it safer, but we cannot force people to write correct code. Ultimately, developers are responsible for removing the bugs from their programs. So, and clearly, any piece of code that correctly uses CPU ID instruction to figure out what features were available on the hardware would never try and run an SSE instruction on your computer that didn't support it. So some notes on the instruction set and binary interface restrictions. I wanted to share with you the most recent validator bug. This was actually found by, let's see, the guy, he goes by the name of Defend the Planet. And if you search for him on Google, you'll see he's actually been around for a little while. He found it after our open source release. And basically what's going on here, this is a place he found where the validator was not checking a condition it needed to check. This is an example of a proper indirect control flow sequence where we have our mask and a jump. In this case here, there's another level of indirection. It turned out I wrote the validator, I wrote this code, I just forgot about this addressing mode. So here we're masking the address of the pointer, not the address that it's pointing to, and here we're jumping to the address that it's pointing to. So not okay. Fortunately, it was just a one-line fix to correct this. But it's an example of, you know, how sensitive this whole thing is. The validator really needs to be very, very, very correct. I mean, it has to be pretty close to bug-free. And that's a pretty high standard to hold yourself to. But you know, it is only 500 lines of code. We managed to get a very compact implementation. And if you think about it, well, you know, gee whiz, the hardware has been decoding x86 instructions correctly for a long time. If they can do it in hardware, we ought to be able to do it in software too. So So that's an example of an interesting bug that we haven't seen any other bugs turn up from the community yet, but I expect there will be more. And I encourage all of you to try and find bugs in the system, just for sport. So that's enough said on the inner sandbox. Let me tell you a little bit now about the outer sandbox. The first question you should be asking is, so you've already got this inner sandbox. Why do you need an outer sandbox? I mean, don't you trust the inner sandbox? Well, the fact is, we think the inner sandbox actually is sound in the sense that it is possible to have an implementation that does the things that we want it to do. The problem is with things, for example, like hardware errata. And those can cause strange behaviors in CPUs that we don't necessarily want to leave the native code without defenses. More generally, there's a concept, of course, and there's always a possibility that there might be a bug in the validator that we didn't catch. More generally, there's this concept of defense in depth, that of having multiple layers of redundant protection for things that are really important. And so our outer sandbox is really an instantiation of that concept. It's a system call filter for untrusted modules. It lives at the process boundary rather than within the process as the inner sandbox operates. It is OS dependent, okay? So we use OS interfaces to implement this. And in particular, on Linux, we're using the ptrace interface to intercept system calls. On Mac OS, they have a thing called sandbox.h, which is a lot like systrace on BSD. It lets you specify for each system call exactly whether or not it can be used and things like that. And then on Windows, they provide an access control list facility that can be used to control invocation of system calls. Now, so then the other part of the question, well, geez, if you've got this outer sandbox, then why do you need the inner sandbox at all? I mean, if this thing works, then, well, we don't really totally trust this thing either. The reason being, firstly, ptrace is designed for profiling, not for restricting system call access. And it turns out that it's quite tricky to implement the security style sandbox using the ptrace interface. And Windows ACLs, there's some holes there too, which I won't go into details, but we know how to break through that too. This one actually is pretty good, and the fact is that if all the operating systems provided a sandbox with a level of integrity, and at least the intention of achieving that level of integrity that you find in Mac OS or in BSD, then it would save us a whole lot of trouble. But systems aren't to that point yet. I guess part of the message I want to deliver, though, is if any of you go off and work for Microsoft or kernel.org, don't forget about this one. We'd really like to see better sandboxing available from the operating system someday. Okay, that's really all I wanted to say about the outer sandbox. If you take a look at our open source release, you'll notice it's not in the release yet. But we're hoping to have it out sometime in the next few months. And the engineers who are working on that are here today. So if you have specific questions about that, we'd be happy to take questions later. Okay, moving on. So I've told you pretty much what I wanted to tell you about how we prevent side effects. Now, it turns out a program that has no side effects is not very interesting, right? It can't actually do anything, literally. So let's talk a little bit about how we allow side effects safely. I wanted to call your attention to a few of the main interfaces that Native Client provides in our current research prototype. The first one we call the Inter-Module Communications Facility, or the IMC. It's a reliable datagram service, and if you take a look at the actual entry points, it'll look kind of familiar. There's sort of, I think it's IMC connect, IMC socket, IMC send message, that sort of thing. Not too different from what you would expect in a Linux socket interface. There are some curious additions, though. Firstly, we make it possible in a native client module to create a shared memory segment and to share that shared memory segment with other systems that are using the IMC. It's represented as a handle, really like a capability, if you will. And when you send a handle to a shared memory segment via the IMC, when it gets to the other side, to whatever other native client module we're talking to, the runtime takes care of actually getting recognizing that it's a shared memory segment and mapping the shared memory into both address spaces so that then you can effectively share. And this, for example, is what we use when we're getting frames out of Quake and displaying them in the browser as one example of a place where you need that sort of high bandwidth communications. There's lots of others. Similarly, we allow file descriptors or communications descriptors to be passed as handles associated with IMC messages. And it's a way that communications channels can be shared between native client modules. So that's sort of the inter-module communication library at a very high level. We also provide a subset of the POSIX interfaces that basically, if you look at it, you'd see open, close, read, write, that sort of thing, the operations that people commonly use on files. Well, wait a minute. If you can't access the file system, then why do you need those interfaces? It turns out they're used for lots of other things, too, like dealing with memory, basically. Above and beyond that, we actually make it possible to open a URL and get a file descriptor back that then you can use open, close. You can't use open. You can use close and read and write on it. So those interfaces are still useful. Then there's a bunch of stuff like mmap and sbreak that's needed to implement malloc, malloc and free. So that's a POSIX subset. We also support pthreads, and we've enhanced it with some synchronization primitives and thread local storage, which you don't automatically get in pthreads. Now, we don't provide all of pthreads. We only really did what we were confident we could do portably with a reasonable amount of effort. But it's fairly complete, sufficiently complete, for example, that we should be able to provide a port of Intel's thread building blocks system that runs on top of native client. And that'll give you lots of nice threading primitives. And then we have a multimedia API that we put on top of the system. And that lets you basically do things like you saw in Quake. So displaying frames, it supports audio, it lets you get mouse and keyboard events and that sort of thing. And those are the main APIs that are provided in the system today. The API is actually evolving over time, and that's a part of why we consider what we have open source today as a research release. The APIs will change as we kind of get closer towards a goal of creating something for broader use. Okay, calling out some specific interesting features of the native client runtime. I already mentioned shared memory. Calls into and out of trusted code go through a mechanism we call a trampoline and a springboard. A thing to understand is within the process where the untrusted code is living, we also have trusted code in the same space that helps with things such as implementing these interfaces that I just discussed. But we would never want the trusted code, for example, to use the same stack as the untrusted code. And the trusted code can see all of the address state of the process, where the untrusted code can only see inside the sandbox. And so the trampoline mechanism actually is a thing that implements this transition from untrusted to trusted code. And it looks a lot like a system call in a lot of ways. There's some instructions to make the rest of the address space visible. There's a stack switch. And then eventually, deeper into the trusted runtime, it'll be copying arguments from the untrusted stack onto the trusted stack and that sort of thing. So that's our trampoline, which is calling out from untrusted code, and then the springboard mechanism is the way that you get back. All hardware exceptions are fatal. I mentioned that earlier. And we actually have layered a simple RPC system on top of the intermodule communication library, but it has very constrained data types. You can use float strings and arrays and opaque handles, but the key thing is that there's no pointers, okay? And if you think about it for a minute, a pointer really wouldn't make sense. Firstly, we're not going to do any marshalling of pointers. I mean, that's just, it's not what we want to kind of propose to support. And imagine that you had a shared memory segment and you wanted to refer to something in that. Well, we make no guarantee or assumption that the shared memory is going to show up in the same place in the different address spaces that can see it. So as a consequence, there's really we're deliberately trying to make it so you can't use a pointer in communicating between different modules. And that's actually an important safety feature, I think, because lots of bad things happen when people use pointers sloppily. So by basically, discouraging people from using them, we think will make the system a little bit safer. Okay, so let's review the different pieces I've told you about and talk a little bit about the attack surface. Where are the places that somebody trying to compromise the system might dedicate some attention? Well, firstly, there's the inner sandbox. And there's both a question of the correctness of the validator that is used to implement it, and also whether or not there's hardware errata that can be exploited to cause the machine to misbehave. Then there's the outer sandbox, and whether or not there's a hole in some aspect of how we do system call interception. There's a binary module loader, because we're actually going to take this untrusted code and load it into memory ourselves. And so, if there was some parameter that was not being checked properly or, something like that, that could lead to problems. There's the trampoline interfaces and the arguments that they take that could possibly be problems. The IMC communications interface. And then also, we provide support in native client for making NP-API calls. This is a way for a native code module to actually interact with the DOM and other parts of the state of the web browser. It's a really, really nice capability to have, but there's one crucial problem from my mind. NP-API was never designed to be used by untrusted code. It was designed for these NP-API modules that already presumably had access to the entire operating system, so there was no point in trying to make the interface safer. Well, we've run into some issues around that already, and I expect that over time, as we find more bugs in browsers and issues with the API itself, that we may have to further constrain how it can be used. So that is the attack surface as we think about it today. And next I want to spend a little bit of time on evaluation. Performance numbers. Here we're looking at the performance of spec CPU 2000 compiled with the native client compiler. Now, it's not using the full native client runtime, but since these things don't do much system calls, it kind of doesn't make any difference. This is an accurate reflection of how performance is impacted. And we're showing you both 16 and 32 byte alignments. We actually support both those options for people who want to create native client modules. And the thing to note is that in some cases, rarely, performance gets better. In other cases, it gets worse. But on the average, and the average is all the way down at the other end, the performance impact is about 5%. Okay, 5% slowdown. So that's pretty good. 5% is close enough that if you were using the system and it wasn't performing quite well enough, you'd probably be better off looking at your own code and tuning your own code as opposed to trying to worry about native client overhead. Now, there are some places where performance impact is a little bit higher, as high as 15 or 20%. Generally, what's happening in those cases is instruction cache pressure. Okay? If you think about for a minute what the native client compiler needs to do to these untrusted modules, it's forcing 32 or 16 byte alignment, depending on the case, for all of the calls and all of the call targets and all the instructions in general, right? And so that forces you to add a lot of no-ops into the program text. And so in the worst cases, we see text expansion of up to 50%. It turns out that for most of these programs, it just doesn't make much difference. The instruction caches on these modern machines are so huge that you can actually pad things out a little bit like this, and it doesn't matter. Now, so that's what's going on. And I have to add that although we've seen this kind of behavior in benchmarks from spec, we haven't yet worked with an application where the instruction working set was so large that we had any performance impact like this. Usually, we really do see things on the plus or minus 5% range. Now, the other thing you might be wondering is, well, if you're adding all these no-op instructions, why would you ever make things faster? And the answer there is alignment. By forcing 32 byte alignment, it turns out we get some positive interaction with the microarchitecture. All the branch predictors and filling out cache lines in a more tidy way, that really interacts in a positive way with modern hardware. And so in the cases that we see performance improvement, that's usually what's happening. It's the benefits of the alignment restrictions. So that's the performance story. And so as the other part of the evaluation, well, what can you do with native client? Well, I already showed you a little bit of chaos in Quake 2. Those aren't really that representative of what we want to do, though, because if you think about, or if you go and look at what we've done, there isn't really any JavaScript or browser activity going on. Those are just C++ applications that happen to be running in this container. So some of these other examples, though, are going to be are somewhat more suggestive of, we really want to complement the web browser with this native code capability. So a Lua interpreter is something that was recently ported, and it went actually out in our open source release on Friday. This is, and the guy who ported it actually, was dreaming of the day when he could just program in Lua and not have to use JavaScript anymore. That's pretty ambitious at this point. But ultimately, a lot of what we're thinking about here, it is about choice, right? We don't want to force people to use any particular language. We want to give them the tools that they need to use any language they want. Anything you can compile into native code or write an interpreter for, we should be able to support. And then these are just other examples of open source libraries that compiled pretty easily for native client and substantial amounts of code. So we're pretty early in this. We don't feel like we've got the application that's going to make large numbers of people want to use native client. But we're happy that the possibility of having fast code in web-based applications is something that people seem to find interesting. So I wanted to quickly mention some related work before I wrap up. There's a lot of prior art in this space. In the field of software fault isolation, the Wabi, Luco, Anderson, and Graham paper is a really good paper. And so if you like this sort of thing, I'd highly encourage you to take a look at that. There have been a number of operating system technologies that have used software fault isolation to allow untrusted or relatively untrustworthy code to be used in the operating system kernel. Vino from Harvard used an approach quite similar to what we're doing, where they had a software fault isolation implementation. Since they were in the kernel, they couldn't use segment registers, and so they had to sandbox their loads and stores and additional sandboxing overhead for their control flow as well. Spin took a different approach. In Spin, they actually used Modula 3, a type-safe language, and achieved a lot of the same properties. And then Nux is interesting because instead of using segments to isolate the memory of these device drivers, it used page-level protection. And that is a very interesting and relevant approach. Probably the best work on sandboxing the x86 instruction set is this work by McCammon and Morissette. And so if you're interested in specifically details about x86 sandboxing, that's a place to look. Now, more recently, there have been a number of systems that have been introduced to do system monitoring kinds of tasks. dtrace from Sun Microsystems basically uses a bytecode interpreter again in the kernel, and it's used for doing performance and for tracing performance and debugging relevant activity in the kernel. SystemTap is sort of the Linux counterpart, and they actually describe a static analyzer that's not that's similar in spirit to what we've done. The XFI work from Microsoft was published in the 2006 OSDI, and it also uses a similar x86 sandboxing approach. And in the most recent OSDI, there was a paper from Microsoft Research about a system called Zax. Zax is very similar in goals to native client in terms of wanting to allow legacy application and legacy C++ code to be used as a part of a web browser. They took a different approach in some ways. They only have the operating system dependent sandbox, the outer sandbox as we describe it. And also, they haven't put any effort into multimedia APIs or things like that we put some work into. So VMs are also very important, interesting work in this space. Again, they're isolating you from the operating system to protect things. We could have thought about using a VM for native client, but the idea of, well, do you download the entire operating system as a part of the native client module, or it seemed too heavyweight. It seemed very heavyweight compared to what we're actually doing ourselves. Now, there's been a certain amount of press coverage about native client, and in particular, commonly they've compared us to Flash from Adobe or Silverlight from Microsoft. That always seemed like a curious comparison. to me. And one example of why is if you take a look at the downloads for those systems, they're on the order of 5 to 10 megabytes. There's a lot of stuff in those. And part of the reason is, if you're getting really comfortable using Flash or Silverlight, you don't actually need to use any of the rest of the browser anymore. You can just work entirely in that proprietary environment. With native client, again, that's not the way it's designed. And in fact, our consumer download, if we were to do one with our current system, would only be about 400 kilobytes uncompressed compared to 5 or 10 megabytes. It's because it's just not doing that much. It's trying to do the minimum possible to make this untrusted native code safer. And in that sense, I kind of think of SSL as being a more relevant point of comparison. Think about SSL. It basically takes an existing protocol, HTTP, and makes it and gives it better privacy. And in the same sense, we just want to take sort of the body of native code that people already use and make it safer by preventing unintended operating system access. So with that, I've finished what I wanted to tell you today about native client, and I'd be very happy to take questions. Amen.
It seems like when I talk to young programmers these days, they all use these managed runtimes like Java and C#, and invariably those are implemented with JIT. And so it seems like that just doesn't work in this scheme at all.
Well, for the moment, yes. We haven't figured out how to deal with dynamically generated code. We've thought about it. We've bounced some ideas around, but it is pretty tricky, especially when you start to work with threads. And it's maybe no coincidence that a lot of the environments that people use for web programming are single-threaded. JavaScript, for example, is single-threaded. From the start of this project, our goal was really to close the gap with native performance. And so threading is one example of a feature that we were just not willing to give up. Another example, which is sort of somewhat more relevant with respect to JITs, is the ability to use hand-coded assembler and eventually vector instructions. From our perspective, there's 1 or 2 orders of magnitude performance gap between the code that uses threads and vector instructions properly and the code that can't use it. And there aren't very many JITs out there that will actually let you do anything with vector instructions. So yeah, it's a very interesting question. I had a conversation with Ben Zorn from Microsoft Research about a year ago, I guess it was, related to this topic. And one of his observations, which I thought was very perceptive, is, during the time when CPU frequency and performance was doubling on a periodic basis, people were willing to give away 20 or 30% performance just, because they knew they would get it back in a matter of months or, not very long. Now we've kind of hit the ceiling, right? CPU frequencies are not really going back up that much anymore. And as a consequence, I actually think, and this was Ben's point originally, that people are going to want that 20 to 30% back. They're not going to be willing to give that away anymore because that's actually the performance that you need to do things like high-definition video decoding or real-time animation for a high-resolution game. So that will be a force that kind of tends to push people. Well, it'll do 2 things. It'll force the performance of these jitting and translating environments to improve, but it will also sort of cause certain people to maybe look more to native code as an alternative for some of their performance-critical computing.
Yeah, people are writing in Ruby and Python, too.
Yeah. Well, I'm looking forward to seeing those get ported to native client, actually.
There we go.
Question?
So this won't work at all in 64-bit because of the segment?
Yeah, the question, would it work for 64-bit? And well, without segments, it won't work in 64-bit. We can't use segments in 64 bits if they're not there. Now, there's a couple of comments I would make, although I'm not really going to tell you, we don't know what we're going to do yet exactly, so I can't tell you what we're going to do. But there was a document presentation for some kernel conference that was published by AMD a couple years ago that talked about adding segment support back to the 64-bit system. And I think it was actually partly because the virtualization people wanted it. I haven't figured out exactly where that's going to go, but that might provide us an option that we could work with. Alternatively, inside of Google, we've been looking at whether there's ways to use the very large address space somehow to do something clever. But we haven't solved this problem yet. And we may actually, worst case, I mean, you might have to go back to a strategy like sort of the classic software fault isolation with much heavier instrumentation. Of course, if that had more than a small performance hit, then you would be better off going with the JIT. So it's a tricky question. We don't really know exactly what we're going to do yet. If I had my choice, I would just persuade the OS vendors. Actually, we'll stick with 32-bit extensions for a while. And because you don't really need a 64-bit extension until you have more than 4 gigabytes of physical memory. I don't think that's going to happen right away. I think we got at least a couple of years before people will want that much memory in this kind of context. Other questions?
Historically, people have had a hard time correctly calling security facilities, especially when there's porting issues and slightly different semantics. And so it's been hard to use curate jails and changing relevant vectors to ID correctly. Could you talk about how you can help these people that will be writing trusted modules? It sounds like lots of random trusted modules are an important aspect of what you do.
Right. So the question for the video was how can we support people who want to write trusted modules and help them get those correct? And the answer is our main focus today is to make the untrusted module environment, sound, that people can't get out of it. We actually are not really encouraging people to write trusted code, and when they do, they'll basically have to go through the same kind of process that native client is going through now to make sure to try and achieve a level of safety appropriate for this kind of application. So we don't have a simple solution. Now, one thing that we are trying to encourage and explore is the more code you can put into the untrusted space, the less you have to worry about how safe or unsafe it happens to be. And so we are definitely working with the people we engage on this to encourage them to put as much code as possible into untrusted space. But there isn't really any simple solution to the trusted part. I mean, for making trusted code secure. Code reviews, peer reviews, open sourcing it so the community can look at it really hard. Those are sort of the best things that I'm aware of. Question.
2 questions. Number one, does it currently support, or do you have any expectation of supporting 3D APIs like DirectX or OpenGL? And number 2, you had mentioned that from within the native a module you can access the DOM and such things. What about if I was in JavaScript and wanted to go into a native client module and pull something back out? Do you have any plans for something like that?
Okay, so the first question was about supporting 3D APIs like OpenGL. That's a really cool idea, and we don't have anything to tell you about right now. So there actually, I did read about someplace somebody porting I think it was Mesa, getting Mesa to build inside a native client. But that would be unaccelerated, so it'd be very slow. So I don't know if anybody, but you could certainly do that. So yeah, it's a very interesting question. The second question was, is it possible to call from JavaScript into native client and pull something out, like a DOM object, for example? And that's actually the easier direction. The harder direction is going from the native client module into the browser. And the problem is that the browser is fundamentally single-threaded. The DOM access is basically single-threaded. None of the browsers really know how to do multi-threaded DOM access right now. And but then the other direction is relatively straightforward. Now, and I think if you look at the examples that we have on the website, you'll see a number of places where we're passing stuff out. While we're all standing here, I just thought I'd flash up my slide of opportunities to do fun stuff with native client. Other questions?
What about resources such as files and sockets, and what kind of sandbox functions are you putting around those? Because a lot of, even with the Quake game, for example, needs temporary files to maintain its current state.
That's a really good question. Let me start just by saying in native client, we're really focused on the CPU and making the CPU available as a resource as directly as possible. And other resources like the file system or the network are not a part of what we're really focused on right now. Well, that being said, I mean, obviously, part of what we'd like to be able to do on the file system side is just use the cloud. And Quake is an example of that. It actually is set up so that it can pull down all the graphics that it uses to initialize itself through the browser by opening URLs. So that gives you sort of a really big read-only file system. Kind of awkward to use still, but I think it will probably improve over time. I actually think that there's a lot of interesting research to be done in terms of other resources above and beyond the CPU, and we just really haven't had time to work on those very much yet. So it's the kind of thing that I'm really excited about the possibility of other folks working on. Actually, I think David and some of his students are already thinking about some possibilities, and yeah, I think it's a very interesting area for research. Other questions? No? Okay, well, thank you very much, and I'll be here for a while, and the rest of the team if you have more questions.